Hi everybody and welcome. Today we're going to be talking about imaginary numbers. So your goal after watching this video will be able to understand, define, but also solve some questions that involve imaginary numbers. So let's take a look first. You're like, Mr. R, imaginary numbers, what are you even talking about? We're working with real numbers. Well, imaginary numbers actually do come up in real life. So if you're an Office fan here, this is Dwight saying 1 is the loneliest number, but false. Imaginary numbers are even more lonely because they don't even really exist. And that's actually not totally true because they are used pretty frequently. If you work in, I don't know, I think like doing anything with like electrical engineering, alternating current, with the alternating current, you're going to be using imaginary numbers. I think the symbol that they usually use is J for imaginary numbers there. So if you've seen that before, that's what they're referring to. And also other science applications like physics with uncertainty involved with the actual placement of particles. Again, you'd be looking into when you're solving imaginary numbers. So while they are imaginary, they are important in many of the sciences that you maybe have already seen in your lab, or maybe that you will be seeing in academics and at any point here with some future science courses. So important skill to know. While they are imaginary, they are definitely real and they are definitely used. It's going to be our job today to go through and kind of define some of those things and get comfortable working with them. So first things first, let's get that definition in here. So imaginary numbers, again, that's what we are working with today. And this is just basically saying when we have the square root of a negative real number. So we know something like if you have the square root of 16, well, we can break that down. We know that 4 times 4 is 16. But if we have the square root of negative 16, nothing times itself exactly equals negative 16. This doesn't exist. Because again, if you multiply 4 by itself, you get positive 16. If you multiply negative 4 by itself, again, you get positive 16 again. So this is where actually imaginary numbers come in. It doesn't exist, sure, but we now have a way to define answers because, again, we know the root of 16. We know that 16 is a number that we can take the root of. Just that negative sign is what disqualified us from being able to do it before. So now we're going to see something like the root of negative 16 is going to give us 4 as the number, but it's imaginary, so we put a little I there. We're going to go through mechanics of breaking down what actually makes it imaginary. How do we decompose these roots step by step next? But I just wanted to kind of give us that idea and show us the concept. It's basically just the same thing as taking roots, but now we're involving negatives, where previously they wouldn't have existed. All right, so let's work through a couple of examples here. So first things first, I know we just mentioned this, but the root of 16. Choosing a number like 16, even though most of us can probably see that it is 4, let's not forget how we have always done this. We've always broken this down. But an extra step here, we're going to take a negative out of it right away. So we have a negative 1. We're going to take that root of negative 1 out. And when we do that, we're just left with positive 16, which means we can deal with this root like we normally would. So something like 8 times 2. Then we can break down 8. We can break down 4. And again, our invisible number here is 2. So we're looking for pairs. So we're left with one pair of 2s, a second pair of 2s, and then we're left with this. There's a root of negative 1, which you know doesn't exist. Well, the root of negative 1, we can define that as exactly I. So we are rewriting this here as I. So our final answer is 2 times 2 times I, or just 4I. So that's what we're looking for in these solutions here is whenever you see that negative, basically means you're going to be taking a root of negative 1 out. It means you're going to be taking, essentially, an I out. So let's do that again here. So again, root of negative 1, that's the I that we're taking out. And otherwise, we can break down 64 like we normally would. So something like 32 and 2. And again, decomposing these to their prime factors like we've practiced so many times now. But again, some good extra practice here. So looking for groups of 2, let's see what we got. 1 group, 2 group, 3 groups. And it just kicked me out here, but that's all right. Our third group, and then we also can't forget we have 3 x's and 2 y's. So a group of x's, a group of y's as well. So what all are we taking out? Well, we have our I, we have our first 2, our second 2, our third 2, an x, and a y, and then can't forget this guy all by himself has to stay home. So this would be our final answer, or we can just rewrite this as 2 times 2 is 4, times 2 is 8. So we have 8xy, and that I is still there, and then the root of x is still there. So we're decomposing these just like we would before. We're just basically adding an I in there. All right, so let's get down to the mechanics of this I term and what we're looking at here. Well, I is equal to the root of -1. That's what we were just factoring out. So let's take a closer look. What happens if we have something like I squared? Okay, well that just means it's I times I, or 2 i's, right? And we know that roots cancel, right? If there's 2 roots and you have a negative number, they just cancel. So we're just left here with a -1. And that's it. So I squared equals -1. And we can actually keep applying these same mechanics to exactly how they were from the question above. So I to the third power is 1, 2, 3. And again, we have our pair here, which gives us our -1 that we can take out, but we still have that root of -1 left. Or we can just simply say this is the negative root of -1. Well, okay, we know what the root of -1 is, though, and I'll point it out to us. The root of -1 equals I. So we're going to replace that here. So our final answer for this one is actually -I. So I to the third power is -I. Okay, let's do this one more time. -1, -1, -1 4 times. Let's get those pairs. 1 pair, 2 pairs. So our first pair and our second pair, and it just equals +1. So a very simple way to define this is I equals the root of -1. I squared equals just -1. I to the third power is equal to -I. And I to the fourth power equals +1. So that's a grid of things you should definitely keep in your notes because you're going to be using them quite a bit. So let's take a look. Where does this come up? Well, if you're just multiplying like you would multiply normal things, 3 times 4 is 12. I times I is I to the second power, except this is no longer simplified. You can't have an I squared there. So 12 and then I squared, well, we know that that equals -1 now. So this just equals -12. And that's actually pretty powerful because we just went from 2 imaginary numbers and we made them into a real number. We made them into just -12, no negative roots involved, nothing imaginary, just, again, -12. So that's going to be your job when you're going through and calculating, is if you ever have anything bigger than I squared, I cubed, I to the fourth, I to any power, we can break it down just like we did in the top examples. We can simplify it, and we can get it to the point where, again, maybe we might even make it a real number. All right, everybody, so imaginary numbers can be a little bit complex to think about, but that being said, if we follow our properties, we keep our definitions close, we'll be in good shape for solving. As always, any questions, feel free to reach out, and I will see you in Teams soon.